Hey everybody, good evening. Welcome to the virtual night sky, our version of the virtual night sky for October the 5th, 2022. I want to welcome everybody that's here tonight. We always have new guests, and I want to make sure to acknowledge, thank you very much for joining us for the first time. And we always have people that follow us from, have been with us for about the 2.5 years we've been doing this program. So I want to say hello to you and welcome. Hey, tonight we've got a great show. We always do. And tonight we're going to be talking about the moons of Jupiter, especially Europa. And so the entry music, anybody know? Of course, yeah, some people knew that was Holt's The Planets, or from Holt's The Planets, and that was the one is Jupiter, bringer of jollity. So, if you want to listen to the whole thing, I think it's something like 14 or 15 minutes long. So, it's a good one to start with, and it's about tonight. So I'm going to introduce in a little bit, first for part of the show, I'm going to introduce a very special guest, and he is actually working on a project that is heading towards one of the moons of Jupiter. And so we'll talk about that and what that means. But then the middle part of the program, I really want to talk about sort of observing Jupiter, what you can see from your backyard and how that looks and what kind of equipment you need and what you can see, what you have access to. And so it's about Jupiter, and there's good reason for that. And then we've got a couple of updates. Who heard about the DART mission, right? Crashing something into an asteroid. And so Armand is going to tell us about that. And then a brand new image was released by Webb today. So there's a gift that keeps on giving. If you can hear noise in the background, it's because I'm outside. I just want to show you something real quick. Before we get started, let me see if I can do this. Hang on just a second. I've got, that looks like your solar system, but this is going to look like the moon. I've actually got a live camera, and sorry, there's a garbage truck driving through the neighborhood. Who knew? And so the camera is actually on the moon right now, but the intent is to be able to show you Jupiter basically from a camera and see the clouds moving by. Right now, from my location, I've got a great view of the eastern horizon. Unfortunately, I've got a great view of a bunch of clouds in the eastern horizon. So the moon is poking through, but sometime during the night, I hope this clears, and I hope we actually get a live view of Jupiter. On the other hand, it's nice to be outside. It's cooled off. It's actually a beautiful evening. And when we first started kind of thinking of this show and conceiving a sort of like how this is going to work and what we're going to do, we really felt like being outside and seeing the night sky and looking at what you can see and doing it together was really an important thing. So I'm celebrating that tonight. The rest of my colleagues are all indoors. And so you've met us all at some point, but let me do some introductions. My name is Rick Alling, and I'm the manager of outreach programs for the School of Earth and Space Exploration. And mostly about what happens at the building, but we also started these live broadcasts, these virtual programs, and we've been keeping them up ever since COVID, and we're going to do it as long as we have an audience. So thank you for joining me. Kim Baptista is our webmaster. She's the one that gets it organized. She gets it out there. She gets it published, and she is the one working in the background to get the technology working in the background. And I appreciate Kim for all she does for us. Meg Hufford is my colleague, and she and I have been kind of working the building for over 10 years now. Tomorrow, we're celebrating the 10th anniversary of the opening of the School of Earth and Space Exploration headquarters. We call it affectionately ISTB4, or Interdisciplinary Science and Technology Building 4. We have a gallery space there. Many of you have visited us. We're going to have you back. Things are opening up, and we're going to have some events that you can participate in. I'll tell you about the end of the show. But Meg and I are still the ones that do that. Two students are with us tonight, Alex Blanche and Armand Dalla, and both of them will have a role in the show, and they're always with us, and we'd love to have them back. We'd love to have them part of this. There is a couple of housekeeping things. We run this in a webinar format, so there is no chat. We don't do that part, but you can interact with us, and we want you to. So if you have a thought, if you want to sort of ask a question, you do that by using the question and answer button at the bottom of your screen. Just push it on and just say, I've been wondering about this, or did you say, or would you talk more about whatever? We'll do it. We'll just sort of answer. And Alex and Meg and Armand are working that in the background. So they answer questions as they come. We'll bring some audience questions to the table about mid-show. We'll take a little break. We'll get you guys participating in some polls, and we'll do a little question and answer. So all of that's there. We do closed captioning, and we do that because it's easier to to make the program, and we upload these to YouTube. If you don't want that, you're in charge. You can turn it off. You don't have to have it on your screen. But just know that we do that. And I also wanted to just do a special shout out for some friends of ours. We were able to go do a program, a lecture last Thursday at Mirabella. Mirabella is a facility near the campus, and it's a living facility. It's a senior living place. It's really associated with the ASU and what we do. And we know some people from there have been watching us overall, but Alex and Meg and I, we went over and we did a program, and they just loved it. We love them. I think that was really great. So if you guys are watching tonight, this is a chance to say, yay, we're here. Mirabella is here. And thank you guys for hosting us a week ago. We felt welcome, and it was a really great show. All right, before we do anything else, I just want to sort of set up tonight. This is your night sky. Of course, this is a simulation, and I will be sort of watching for Jupiter if I can get it on a real camera. And if I can get it on a real camera, I can show you Jupiter, I will. But this is a simulation of what we're looking at. And Jupiter is in opposition. I'll tell you about what that means later, but just note that it is bright. It's the brightest thing in the night sky aside from the moon. It is star-like object, and it's almost directly in the east, right? So you see here, you have the horizon, and you see the eastern part of the sky. You won't see Neptune. It's too dim for you, but the moon and Saturn and Jupiter, if it wasn't cloudy tonight, they would look exactly like that. That's the position they would be in. Now, with this little trick of technology, I'm going to do something. I'm going to sort of like highlight Jupiter. I'm going to center Jupiter, and I'm going to zoom in. We're going to fly out there. Here we go. And notice what's coming into view here is that there are 4 moons. More about this later. I'm going to be talking about Galileo and discovery of the moons, but I just really wanted to point out for this particular moment, the 4 moons, we call them the Galilean moons now. I'll explain that later, that we can see are Io, Europa, Ganymede, and Callisto, and they orbit around Jupiter. And if you have a little pair of binoculars, if you have a small telescope, you can actually see these. It's really, really accessible, especially with today's technology. It's easy to see. Tonight, we are focused on Europa for the most part. Europa is a moon of Jupiter, and this gives me a really, really good opportunity right now to introduce my guest, John Hill. John, I've known you for, oh goodness sakes, must be about 10 or 12 years, I think. John was a student in the School of Earth and Space Exploration, and I'm going to let him explain what he does now and his role and how he's connected to Europa, and a very, very exciting mission to go up and sort of visit Europa. So I'm going to ask John to come to the screen and tell us a little bit about yourself, and tell us about Europa. Why are you working on it and all of that kind of stuff? Hi, John.
Hi, Rick. Thanks for inviting me to come talk with everyone today, and welcome to all of our visitors. So yeah, a short introduction about myself. My name's Jonathan Hill. I work at ASU at the Mars Spaceflight Facility, although that name is becoming a little inaccurate. My history is I've worked the last 15 years or so operating our Ethemus Camera, which is an infrared camera orbiting Mars. And what I'm going to talk about tonight is that we've taken basically the technology and the science behind our Mars Ethemus camera, and we've rebuilt it to instead go to Europa and look at what is possibly the most interesting moon in our entire solar system. If you don't know, Europa is really special because it is completely covered with ice, and beneath that ice, which we don't know exactly how thick it is, there is a liquid water ocean. And so when it comes to other places in our solar system that might have life, Europa is really high on that list. And that's one of the reasons why NASA is sending a new mission there. It's called Europa Clipper. And our Ethemus, which stands for Europa Themis, is going to be one of the payloads. And so, Rick, I will go ahead and share my screen.
Absolutely.
Okay, just checking, Rick, you can see that okay?
Yeah, John, it looks great. Everything looks good.
Okay, so just to get started here, I want to talk about wavelengths of light. So our eyes as humans can see what's called the visible light spectrum, which is right in the middle of the graph there. If you go to the left to beyond purple, that's where you get the ultraviolet wavelengths. So that's what causes, sunburns, and sometimes you can get black lights which show UV to make certain rocks or animals fluoresce. What we're going to talk tonight is about the infrared, which is if you go to the red side of the spectrum and go past red. So what we're talking about is colors that are redder than red. And once you get into the infrared, you start seeing heat instead of actual color. And so this is an infrared image of two humans, and you can see based on the temperature of their skin and clothes, infrared cameras can see exactly how hot or how cold they are. And so we're able to measure temperature either from a couple feet away or even from hundreds of kilometers away. And so this is basically the same technology that you might have at home if you have a non-touch infrared thermometer to measure your temperature. You just point it at your forehead and it'll measure it. This is what happens if you have a camera that can see hundreds or thousands of infrared points. So now to introduce our Ethemus camera, I'm going to show a quick video from our principal investigator, Dr. Phil Christensen. He's the primary scientist behind both the Themis and the Ethemus camera. And this will be him just giving a short explanation of what it is and what science we hope to do once we get to Europa.
I've spent most of my career studying Mars, and Mars is like the Earth. It's rocky, it has mountains and sand dunes. Europa is completely different. It's extraordinarily cold. The surface is covered with ice. I'm Phil Christensen, a professor here at Arizona State University. I'm actually what's called the principal investigator of the Ethemus infrared camera. The key question that we have for Europa, which is a moon of Jupiter, it has an ocean, a liquid water ocean under a thick crust of ice. And the key question is there life in that ocean? It'd be very rough. It'd be like walking on broken, jumbled, blocks of ice. And then underneath all that ice is this warm ocean. So what we're trying to find out is how close is the ocean to the surface. Our camera, it's an infrared camera. We all have cameras. They're on our phones. Those operate at visible light. That's what our eye sees. But there's a lot of other light. There's infrared light. And so Ethemus is an infrared camera. It's a night vision goggle. So you've seen pictures, taken at night. We can see in the dark because everything is giving off infrared light, and that light is associated with heat. And so the hotter things are, the more infrared light they give off. Europa is covered with these fractures. The ice is moving around. It's like, Arctic ice on the Earth that moves and moves. Because the ocean is churning and moving underneath, if that warm water comes near the surface, our infrared camera can detect warming patches of ice. And so what we're trying to figure out is the water near the surface, is it erupting onto the surface? If it did, we'll still see warm ice with our infrared camera. We've built a camera. We're going to take it to the Jet Propulsion Lab. They're going to put it on a spacecraft. It'll launch on a rocket out of Florida in October of 2024. Jupiter is a long ways away, but it hopefully will be worth the wait.
Okay, so as Phil was just saying, this is an example of an image, an artist's rendition, obviously, of the Europa Clipper spacecraft that will eventually get to Jupiter. And it's actually going to be an interesting orbit. It's going to orbit Jupiter itself and just do short flybys of Europa. And we're going to do that for two reasons. One, if we had to slow down enough to go into orbit around Europa, we'd have to carry a lot of extra fuel with us, and that would make it a lot harder for us to get there. Also, it turns out that the area around Jupiter is just saturated with radiation, the type of radiation that will kill spacecraft very quickly. So the estimates we've done is that if we went into orbit around Europa, the spacecraft would probably only last about a month, which is way too short. So instead, we're going to go into orbit around Jupiter. We're going to dip into those radiation belts really quickly, fly past Europa, take a bunch of data, and then quickly fly out of those radiation belts. And that way we'll have a bunch of time to downlink all of our data, get commands up to tell it what to take pictures of next, and then we'll dive back in again. And so we'll be doing that on about a 2-week cycle. Every 2 weeks, we'll make a really close approach to Europa, swing back out, send all our data back, and then get ready to swing back in again. Now, like Phil said, the Ethemus camera is looking for warm ice. And so what we hope is that we're going to get pictures down like this. So if you look at the surface of Europa, it's covered with all those cracks. And what we think is happening is that the water, the warm water underneath, is welling up and pushing the ice apart, almost like tectonic plates on Earth are pushed apart by rising magma. So in this case, we think the ice plates on Europa are being pushed apart by warm liquid water. And I'll just point out the temperature scale there. When I say warm, that's very relative. So we're going to see very cold temperatures there. At the hottest end, like you see on that sample image, we're expecting to see ice that's about 200 Kelvin, which is about -100 degrees Fahrenheit. That's probably the warmest thing we have any possibility of seeing. In reality, we'll probably see stuff much colder, maybe -120, 150 degrees Fahrenheit. But as long as it's warmer than that surrounding ice, that tells us a lot about how that ice is moving around. So here's a picture of Dr. Christensen actually holding part of the Ethemus camera in his hands during assembly. And I'll just note that that little camera there is extremely hard to hold. You probably can't tell from that picture, but Phil is really straining there. It's just barely liftable. And the reason is that all that radiation, to protect the camera from all that radiation around Europa and to make sure we can take good pictures despite the radiation, we had to build in a lot of shielding around the camera electronics. And so that is just a huge block, basically, of copper tungsten, very dense, very heavy, just to protect the little camera inside. So after we built the camera, this is a picture of us, we put it into that large silver cylinder back there. If you come to the CC building, ISTB4, you can see we have a big wall of windows into our clean rooms, and you can actually see our scientists working with this chamber and other test equipment in the clean rooms. And that's where we pump all the air out, we chill it down really, really cold to simulate what it'll be like in space, to make sure the Ethemus camera will actually work in that environment, because it's going to be a very different environment than just the rooms where we're building it. Now, after we finished it, we wanted to test it out, because unfortunately in that big silver chamber, we can do a lot of tests, we can make sure everything's working properly, but it's really hard to get a good image of something because everything in that chamber is really cold. So as you see here, we put Ethemus, which is in that top little silver bag there, along with all of those electronics and cables. We bundled everything up, protected it really carefully, and took it up the elevator to the very top of our building and rolled it out onto the patio. And so we could actually see the Tempe skyline and get a picture of it in the thermal infrared with Ethemus to prove that the camera was actually able to take actual images rather than just seeing the temperature calibration targets in the thermal chamber. And so you might have seen this picture in the video. This is a picture of the Tempe skyline. On the left there, you can see a mountain. Just below that, you can see the boxes of Sun Devil Stadium. And just to the right of center there, the little building with all the triangles, that's the Manzanita Residence Hall on the Tempe campus. And as you can see, we did 3 images, one at about 12:40 in the middle of the day when the sun was out, everything was warm. Again at 4:40 p.m. and the sun was still up, but it was much lower on the horizon and the city had begun to cool down. And then we did a third picture at 6:20 just after sunset. And you can see that a mountain has really cooled down, the buildings are cooling down really quickly. And so these 3 images, a set of images, prove to us that not only can Ethemus measure temperatures really well, but it can also produce really clear images, which is what we want when we get to Europa, to see the temperatures of those ice fractures. So after we took it up to the top of the building, we had to clean it off, very, very clean. Since we're going to a moon that could possibly have life on it, we want to be very careful that we don't take anything from Earth that's living with us, or anything even that has organic residue with us. So we had to be extremely clean during the entire process of building the camera, and we had to re-clean it constantly throughout that process. Now, this is kind of an interesting picture. This was just a couple weeks ago. We put the Ethemus in that little blue carrying case you see Ian and Zoltan holding there. And we actually shipped it to the Jet Propulsion Lab in California with FedEx, which was a first for us. Usually we actually hire a private plane and we fly it directly to wherever the spacecraft is being assembled. But in this case, JPL was such a short drive from us, and we decided it was actually safer and less risky to drive it rather than putting it on a plane and flying it there ourselves. So there's a special service that FedEx offers that's a very, very careful transportation system. And their special drivers will take it for us, and we follow behind in our cars. And this is a picture about 8 hours later, delivering it to the giant clean room at JPL. So that large building behind the FedEx truck there is where they're assembling the entire spacecraft and where all the instruments are being delivered to. So this is us inside that clean room. Once we'd taken the carrying case inside, unboxed everything, this is the little Ethemus camera with its plastic bag on top to make sure nothing falls into the camera itself. And if you look really carefully at it, you can see those 2 little black plates. Those are the signatures of everyone who worked on the camera or who will work on it once it gets to Europa. Dr. Christensen has been really good throughout all of the years, his years at ASU. Whenever he builds instruments, he always has everyone sign their name on a little plaque so that you can say that your name at least got to go to all these wonderful places throughout the solar system. Now, if you'd like to watch the JPL staff building the Europa Clipper spacecraft, they actually have a 24-hour YouTube stream of the clean room. And so this is a screenshot I took earlier today. On the left-hand side with that sort of copper square, that's the main body of the Europa Clipper spacecraft. Right now they're assembling all the fuel tanks, all the computers, and once they get done with that in a couple months, then they'll add in all the instruments. And there's going to be 10 instruments, of which Ethemus is just 1. And then on the right side, you'll see there's, on those blue supports, there's a little round piece. That's the very base of the spacecraft. So once that piece on the left is pretty much done, they're going to attach it to the base, and then they'll be able to wheel around the entire spacecraft on that support structure to get at whatever piece they need to work on. And I know it's a little long. That's the permanent link on YouTube down at the bottom there. However, if you just search YouTube for JPL Europa or Europa Clipper, this should come up as the first suggestion. And sometimes it's a little slow. There's only a couple people working on it at a time. That's because they like to take their time and really be careful with everything they do. And as you see, they're all working in what we affectionately call bunny suits to make sure that the entire spacecraft stays extremely clean while they're assembling it. So that adds into the difficulty and slows down the work a lot. So you're never going to see anything really exciting happening on this YouTube feed. But if you check in day to day over the next couple months, you'll see them adding major components to the spacecraft. Now, as the video said, we're going to launch to Europa on a Falcon Heavy rocket from Florida. And if you've seen one of the Falcon Heavies launch before, I think there's only been 3 launches so far. Those 2 side boosters will help get it going really fast and then will come off. And then the center booster will continue taking it into orbit and beyond. And the really cool thing about the Europa Clipper mission is that if you watch SpaceX launches a lot, you'll notice that they usually land the side boosters and even the center booster. But for the Europa Clipper launch, the spacecraft is so heavy and we're going so far that we're actually going to be the first time SpaceX is going to launch this rocket in its fully expendable mode. So we are going to use every last drop of fuel in this rocket. And so we won't be able to land any of the 3 first stage boosters. Those will all just have to fall into the ocean and crash because they won't have any fuel left to try to land. We will have already used it all. And this is the schedule as it stands today. It's obviously subject to change, but we're planning to launch in October of 2024, so almost exactly 2 years from today. We will do a flyby around Mars that following February in 2025. That'll help us speed up. And then we'll do another gravity assist around the Earth in December of 2026. And that'll get us going really, really fast. And then we'll slingshot out to Jupiter and get into orbit around Jupiter in April of 2030. So this is a very long-term mission, and the entire staff that's working on it, all the instruments and the spacecraft itself, we're having to pace ourselves because this is going to be a very long-term mission. Now, in closing, I want to talk about some recent news. Less than a week ago, another NASA spacecraft that's also currently orbiting Jupiter, called Juno, was able to fly by Europa and take some really good pictures. Now, the Juno spacecraft, which you see here, is actually at Jupiter for another reason. It's there to study the atmosphere of Jupiter itself. So it flies around Jupiter, swings in really close to get really good measurements. But in the past, it has specifically avoided the large Galilean moons, of which Europa is one. However, they're now in their extended mission, and so they adjusted their orbit slightly so that they could fly by some of those Galilean moons and get our best data on those moons since the Galileo probe in the late 90s. And so just about 5 days ago, it did its closest approach yet to Europa. And this is one of those pictures. You can see it got really, really close, has a really high resolution view of all those ice cracks that we're going to look at with Ethemus and hopefully see them being warmer than the surrounding ice. And then I'll leave you with this global view that Juno got of Europa. That is probably going to be the last really good view that we humans get of Europa until the Europa Clipper mission arrives in April of 2030. And with that, I will turn it back to Rick.
Actually, why don't you hang on for a little bit? What I'd like to do is just kind of ask you some questions myself, and then we'll try to turn it over and take some audience questions as well. But
Oh, absolutely.
I think this is, thank you very much for the presentation. I think this is a really, really good overview of exactly what we're trying to achieve. And I just love seeing that video with Phil Christensen. I'm not sure the audience sometimes, or we've said it before, but you might forget, is that our ability to actually produce space grade instruments and devices and things like that on the ASU campus is actually kind of unusual. Most universities can't do this. And then those spaces, as John described, are sort of like right in our lobby. So you can kind of come and watch, and sometimes you can see people working in there building these things. And so what a great opportunity for you, right? I mean, so how did you get involved with this? And then how do you get into the clean room, and how do you become part of like building something that's going to go into space? I think it's amazing.
Yeah, so we're actually one of very few universities, like you said, who can build instruments actually completely on campus. Normally, when universities design instruments, that's all they do. They design them and then send it out to a big aerospace company like Boeing or Lockheed Martin or Raytheon to build the actual instruments. And that's something that Dr. Christensen has been really adamant about the last 20 years, is really building up the capability to build our own instruments on campus ourselves. And so Europa Ethemus is actually going to be our 4th instrument that we've built on campus. And this was definitely the hardest one so far, because it's going to such an inhospitable, far away place.
I'm sorry, I heard you talking a little bit about sort of the nature of the radiation around Jupiter, and I've heard this before, and I kind of understand how you really don't want to be flying around Europa, because that's where all the radiation is. So this is actually an orbit around Jupiter and a flyby of the moon. And how many passes do we get? I mean, is this indefinite? How many times can we fly by this object, and what do we get to see?
Right, so the primary mission, which is what the spacecraft is designed to handle, is approximately 50 flybys. Okay. So on a 2-week cycle, that means we'll spend about 2 Earth years every 2 weeks dipping in really quickly, getting a view of Europa, and then scooting out of the radiation belts. And, you know, one of the things we've unfortunately gotten used to over the last 20 to 30 years is NASA missions lasting way longer than they were designed to. Right. You know, for example, the Mars Themis camera that I spend most of my time working on launched to Mars in 2001, and we're now 21 years later. We're coming up on in a couple days our 21st anniversary of arriving at Mars, which is just incredible. And so
that's amazing. Okay,
so
how old were
unfortunately
how old were you when I'm sorry, how old were you when they arrived at Mars then? If this is the 21st anniversary, come on.
So I was actually a sophomore at ASU in aerospace engineering. Okay, and good. I actually remember watching the Webb feed, because this was the first time that NASA did a webcast for a spacecraft event. And I remember watching on my computer Odyssey going into orbit around Mars, and then getting right back to my engineering homework. So but yeah, Europa Clipper is probably going to be different than a lot of these missions, and is probably not going to last very long beyond its primary mission. It's definitely not going to last 21 years.
Just because of the hostile environment, right?
Yeah, because of that hostile radiation. It's going to take everything we've got just to survive those 50 passes. We might get 51 or 52, but probably not much beyond that.
Good. And are you working on other things along the way, or is this your primary thing? This is the one you're doing? Or...
Yeah. So right now I'm working on a lot of different missions. My part of Ethemus, I wasn't part of the build team, so a lot of our engineers, like I showed, were involved in actually building it. I helped a little bit with testing, but my role won't really come into effect until after we've launched, because I do mostly mission operations once something is already in space. So we've started practicing how we're going to send commands to Ethemus and get pictures back. but we won't actually start doing that until probably 2025. So until then, I've been working mostly on Mars Themis and our OTES instrument that's on the OSIRIS-REx mission.
Excellent. Well, that's very good. And then I don't know if you have a slide or a picture or something, but I just so let me just say, we're going to open this up to audience questions. And so I'm just about to kind of ask the team to come to the table and give us maybe some questions. But while they're getting ready, and I'll remind the audience that you can ask questions, right? Push that button and do that. But there's something I know about you, John, that I just thought was really, really wonderful. It has nothing to do with this, but I'll just tell the audience. John sort of managed this project where we made this gigantic image of Mars, like that lays out on a basketball court. And I don't know if we have any pictures of that. Do you have one you can show people what's going on? And then where did that come from? Where did the idea behind that come from?
Yeah, so if you've been at various ASU open houses in the past, you might have seen our giant Mars map. It's the size of a basketball court. And like I said, the Mars Odyssey spacecraft has been in orbit around Mars for coming up on 21 years. And so we've managed to map the entire planet in the infrared. And the idea came is we wanted to show off to everyone basically all our great data. What does 20 years of Mars data actually look like? And the only way we felt we could do it justice was by showing it on this giant vinyl mat that you're able to walk across and kind of explore Mars for yourself. So if you haven't seen that before, yeah, keep an eye out for.
I'm gonna share it. I have.
Oh, okay.
Good.
I'm gonna have to stop your screen from sharing.
Oh yeah, no problem.
I think you guys can see all that.
and this one's on the Capitol Mall, right? This is in DC. Is this one?
Yeah, so this picture is from right before COVID started. We took the giant map to the National Mall and displayed it right outside the Washington Monument. And so we were there for a weekend and just allowed visitors from the mall, as well as some of Arizona's congressmen to come walk on the map and just learn about Mars.
I think it's great. Anyway, well, good. You've got a really long and wonderful history at ASU, and I hope it continues forever. And I just really appreciate what you're working on. I think it's really awesome that this really is an ASU born and bred project. Phil Christensen invented this technology. We built it there, and here we go to this amazing thing. Okay, I'm going to ask Alex to come on and kind of help us understand some questions that might come from the audience.
Yes, we actually have a few questions. We have two kind of combined about the radiation around Jupiter. One, what causes high radiation levels around Jupiter? And then how are the lens of Ethemus protected from that radiation?
Those are both really good questions. So I am definitely not a plasma physicist, but my understanding of the radiation around Jupiter is that basically because Jupiter is such a large planet, very early on in the solar system's history, it pulled in a lot of radioactive material. And over time, that is just decaying naturally, and that radiation gets expelled. But then unfortunately, because Jupiter has such an insanely strong magnetic field, that radiation gets captured in these really strong radiation belts. And so, yeah, speaking about the lenses of Ethemus, they are very protected. The lenses themselves are actually buried inside that big block of copper tungsten. But as you might suspect, the weakest part of that instrument is the lenses, because we can't possibly shield them as strongly as copper tungsten. So that is probably how Ethemus is going to eventually fail, is that the camera detector itself will burn out because of the radiation leaking in its viewing port, unfortunately.
All right, great. And we have one more question, actually from Nicole from the LROC team at ASU, who we're all very familiar with. And they ask, what's the focal length of Ethemus and what's the lowest altitude the spacecraft will reach from Europa, I'm assuming?
those are very good questions. I actually don't know offhand what the focal length is. Yeah, but as you probably saw, it's a deceptively small little camera. You can just hold it up. So it's a very short focal length, but yeah, we'll have to talk sometime and look it up. And what was the second part of that question?
The second part was, what's the lowest height above the surface that the spacecraft will reach?
So I don't know what it is today, but that is very much in flux. As you might expect, all of the instruments on board, all 10 instruments, want to get as close as possible to Europa. And all of the engineers that are in charge of keeping the spacecraft safe want to keep us as far away from Europa as possible. So it's this trade-off. And what's probably going to end up happening is we'll probably start relatively high, a couple 100 kilometers. But then as we kind of get used to the spacecraft, get to know its little idiosyncrasies, and just get better at operating it in this real life environment, we'll probably slowly dial that down. And in the end, we might be able to get within 200 or 300 kilometers of the surface at best, which should give us very good images. Ethemus could get down to 100 meter per pixel resolution, which doesn't sound that great for like Earth imagery, but when it comes to Europa, that'll be some of the best thermal imagery we've ever gotten.
All right, well, thank you so much. Those are the questions from the audience. Rick, we also have some polls. Do we want to launch those now, or do we want to head it back to you first?
Actually, go ahead and launch the polls. I just actually now have a view of Jupiter that I'm actually trying to kind of organize. See that little dot sort of over my shoulder? Let me see if I can point to it right there. That's Jupiter. So anyway, while you're doing the polls, I'm going to try to dial it into my telescope.
All right, so we do have the poll questions launched. We have 2 of them here. How many moons have been cataloged for Jupiter, and how long will the trip to Europa take? Fill those out, and then we'll get back to the answers in a little bit. If you have any more questions, feel free to ask right now when we have the time. Until then, just feel free to answer those poll questions that we have. Looks like we're kind of getting a nice even split for the first one, which is interesting. Usually we don't have almost all answers kind of within a similar range. I'm surprised.
There's no Jeopardy music for Jeopardy Jupiter. Okay, just saying.
Just put the whole suite up again. That's our Jeopardy music now. All right, we're getting close to almost everyone in, so put in those last few answers, those of you who have, and we'll share the results pretty soon. Rick, do you have Jupiter up in your telescope?
I don't, but I do have a little bit of sort of stuff I want to show you here. And then when we take another break, I'll see if I can get it going. So, I just want to kind of show people a little bit about sort of Jupiter and where it is and what's going on. Let me get that out of the way. There you go. You don't need to see that. I'm going to get that out. So how did the audience do here? So gosh, it's like 30, 30, 30. Whoa. 5.5 years. Okay, well, we got that part. Well, we've been listening a little bit. This is essentially your solar system. You guys remember this part? And I just wanted to show you something. I'm going to make Jupiter and the Earth, let's say 1,000 times bigger than they actually are. So you can see kind of their relationship right here. And I'll make Earth 5,000 bigger than it is. And so what you see here is this is the way the arrangement of these objects are right now. You can kind of go, if I go in there, you can see the sun's there, the sun's shining on the Earth. and directly behind us, or almost directly in a line, is Jupiter. And what that means, we call that the term for this is Jupiter's at opposition. The Earth's orbit moves way faster than Jupiter's orbit, and what that means is that the Earth is actually kind of moving in this particular direction right here. And the 26th of last month, so that's only about 8-10 days ago, we were right in between. And what that means is that the Earth and Jupiter are as close as they can be during the orbits, right? The Earth is going to just very quickly sort of move away. Half a year from now, we're going to be all the way over here. We won't even be able to see Jupiter because the sun will be in the way. But this is just the reason to kind of do this program tonight. The reason this is all kind of important right now is that Jupiter is really easy to see. It's very bright. And even for me right now, the clouds have cleared and I can see it in the night sky. I'm going to center Jupiter now. Just so we have a chance to fly out to it, and you'll see the sort of the screen will arrange itself a little bit here, and I'm going to go kind of move out. I'm also going to reduce it back down to its regular size, so it looks like we're flying away, but we're not. And then I also wanted to kind of show you Jupiter's moons. So over out here in this particular part of the orbit, I'm showing you, I've blown up them really big. Let me sort of put some orbits on just so we can kind of keep this in sort of like understanding here. So Jupiter is the little object in the middle. And the 4 Galilean moons, I have brightened really, or I've made them larger so that we can see them. And if I can point to these, I think you guys can see my pointer. I have to stop flying in order to do this. What I wanted to do is just sort of show you. So this is Europa right here. It's the second closest one to Jupiter. This is Io. This one is called Ganymede, and this one is called Callisto. And those are the Galilean moons, the ones that Galileo discovered. There's this old joke. I don't know if you've ever heard it before, but you know, what a coincidence that Galileo discovered the Galilean moons, right? Well, I know it's an old joke. I'm going to just kind of put some graphics up here. You remember this guy? This is Galileo, and it was in the winter of 1609, 1610 that he got a hold of a telescope, and he's starting to like be the first human to look at objects in space. He didn't invent the telescope. It was actually sort of like a spyglass. It was invented by somebody, and it was actually used terrestrially or to see ships at sea. But he was kind of the first scientist to say, you know, this might have some potential in looking at the moons themselves. Just to give you an idea about these moons, this column right here are the moons of Jupiter, and there it is again, Io, Europa, Ganymede, and Callisto. You can see that our moon is of similar size to the rest of these. And you can see that Saturn also has a moon called Titan, and Neptune has a moon called Triton. And the 7 of those moons, the 4 Galilean, that one and that one, Titan, Triton, and the moon, are the 7 largest moons in the solar system. But there are many moons in the solar system in total. Let me just show you a little sort of sketch. This is sort of thought to be from Galileo. And the important thing in here is that you can see that we're sort of like crossing over. This says observing Jupiter 1610 at the top. And this is actually sort of little markings and denotations, you know, by the man, Galileo himself. The circle is Jupiter. And what you can see here is that the moons kind of change position over time. So this is night after night. Here's the 2nd, 3rd, another sort of view later on the 3rd, 4th, 6th, 8th, 10th. This is going to be January of 1610. And he's watching all of this. The important part of that is that he's observing something that has never been seen before, and he's observing moons of something or something orbiting something other than the Earth. And that became very significant. The fact that objects are orbiting something else sort of was the first time ever thought of. Because remember, Galileo lived at a time when we still thought, at least astronomers thought, the Earth was the center of everything, and everything went around us. Everything went around us. So Galileo was able to see like mountains on the moon, and that changed our ideas about what other places could be like. He was able to see phases of Venus, so sort of like this starts to describe a solar system that was hitherto unknown. And he saw these moons. He called them the Medicean moons. His patron was one of the Medici families, right? One of the of Florence, one of the major families, and that was the guy that gave him all his money. He called them the Medicean moons or Medicean moons, and watched them over time and was able to devise this really important factor of moons. And so I think that's about all I have time for. I just wanted to kind of put a little context into what's going on. And I'd also like to suggest that if you have a chance, it would be a really good idea to get out. If this is, I mean, even binoculars will show you these moons, and there, I think, is no better time than what's coming up over the next couple of weeks, right? We are out of the monsoon, so the clouds are going to dissipate. It's cooler in the evenings, so you can get out. Jupiter is very as close to us as it gets, and it's easy to find. I mean, everything is sort of aligned right here to just go check this out. Not only are you looking at Jupiter and its moons, but this incredible rich history going back 400 and what is it, 412 years now that we sort of first started understanding these moons. And then you are armed with this special knowledge, bringing it right up to today with what John Hill is working on in a very particular instrument that is, I mean, that is headed to Europa. Would Galileo ever think that that's even possible? I don't know. One more thing I just wanted to show you. I sort of like put this little image together today, and you'll see when Armand comes on next, that this is actually Europa is the surface on the bottom, and Jupiter is the object in the background. And this is what it would be like to be on Europa, and we're near Europa, we're orbiting Europa and seeing Jupiter in the distance. I'm going to leave it with that for now, and I'm going to invite Armand to come to the table to talk a little bit about the DART mission. So thank you very much for your attention.
Thank you, Rick. I'm going to share my screen and get started. So last Monday, September 26th, the DART mission took place, and it's called a Dharmission Double Asteroid Redirection Test. And this was done basically in preparation of a future asteroid impact for Earth. So asteroids are always hitting the Earth all the time. Most of them are really small, and they just burn up in the atmosphere and don't really touch the surface. Bigger ones, they come, hit the surface, make craters like the one meteor crater in Arizona itself. When they're a lot bigger, they can cause big extinction events like ones that happened 66 million years ago, sorry. And when they're really big asteroids, then we gotta hire Hollywood actors and make a movie out of it. No, I'm kidding, of course, but the DART redirection test was done to check how we would basically prepare in the event of asteroid impact. You may think we could just like fire a missile or a nuke and blow up the asteroid, but that would only cause it to break into a lot more smaller pieces, and those pieces would still be heading in the same direction and hit us on Earth anyway. So the ideal situation would be to redirect the asteroid and make sure it doesn't hit Earth at all. So that's what they did. They built a satellite to go impact an asteroid called Dimorphos. Dimorphos is a much smaller asteroid that's actually orbiting around another asteroid called Didymos. Didymos is about half a mile across, and Dimorphos, the asteroid that's going to be, or that was impacted, is only about 500 feet across. And the DART spacecraft itself is only about the size of a vending machine. So think about a vending machine ramming into an asteroid about the size of a football stadium. And The DART asteroid was actually followed by a CubeSat by the Italian Space Agency to capture the moments of impact as well. And we will see some images from that as well. But one of the cool things about the DART spacecraft was that it had a camera on board the spacecraft itself. And so we were able to see the collision as it happened in real time. So on the bottom left, you can see Dimorphos, the bigger Didymos, the bigger asteroid, sorry. And in the center, you can see Dimorphos, the smaller one. As it got closer, you can go on YouTube and search up the full video of it actually going and hitting the asteroid as well. But here we can see Dimorphos. As it got closer and closer, you can see the surface. And this is the final image it got before impact. And this image was taken about 4 miles above or away from the surface of the asteroid, but only 1 second before impact. So you can just imagine how fast the spacecraft must have been going. And it took the image 1 second before impact. And so during the transmission of the image, it hit the asteroid, which is why we are only able to see a small portion of it. But like I said earlier, DART wasn't alone. It was accompanied by another smaller cube satellite that was able to see the impact. You can see the impact up here with the gas and dust from Dimorphos. And luckily, that cube satellite wasn't the only thing observing the impact. There was lots of ground-based telescopes, as well as the Hubble Space Telescope and the James Webb Space Telescope looking at this one impact. And this is actually the first time ever that both the Hubble Space Telescope and James Webb Space Telescope were simultaneously looking at the same target in real time. And remember, Hubble sees things in visible light, the same light you and I see. James Webb looks in infrared light. Like we were talking about earlier, infrared light is basically heat or thermal energy. And so by looking at the impact in different wavelengths, we're able to see more clearer the distribution of particles, whether the stuff ejected from impact were very small, fine dust, or whether they were large boulders. And along with these amazing images, remember, this was taken over the course of a few hours, condensed down into a few seconds. But these, along with lots of ground-based observations, will really help us learn more about asteroid redirection and kinetic impacts into asteroids itself. And now I'm gonna stop sharing and transfer it over to Alex, I believe, for some new James Webb Space Telescope images.
Yep, absolutely. Alex, what do you got?
Yeah, so a team here at ASU just had a big release of a big James Webb image. There's a short little minute video. I'm going to share that, and you guys will get to learn more about that.
This is one of our first and most beautiful Webb images of a galaxy pair at a distance of about 500 million light years away from us. So I'm Roger Windhorst. I'm a Regents and Foundation Professor at the School of Earth and Space Exploration at Arizona State. And I'm also an interdisciplinary scientist for the James Webb Space Telescope. So there's a dust lane in this spiral, the same dust that our solar system is made from. When it formed a star and 8 or 9 planets. And that you can see here. You can see it's the courtesy of that background flashlight, or elliptical if you wish. We got more than we bargained for. Not only is this a rather unique alignment of an elliptical in the background and a spiral we're trying to measure in the foreground, but you see this funny arc-looking object. That's a galaxy. That's a galaxy like this one or that one in the background, seen within the first few billion years after the Big Bang. But its light is gravitationally distorted by the enormous mass of this elliptical galaxy, which is close to
the mass of 1 trillion suns. I'm telling you, you've seen nothing yet. A lot more of this is coming. We have about 18 targets with Webb the first year, and the ones that are coming, stay tuned. It will be mind-boggling.
Sorry, that's excellent. I'm still trying to get Jupiter sort of like in line here, but it didn't pop into the clouds soon enough for me to get organized so I could show it to you. But I am going to kind of bring us to a close. I've got a couple of announcements of some events. Tomorrow night, we have New Discoveries Lecture Series, and the fall program is available. You can come see us at the school at the ISTB4 building at 7 o'clock, or you can get it online. And so there is, we'll put into the chat the link to be able to do that. So there's an online component and then a live component. And this is actually Evan Scanapieko, which is he's a professor that I've enjoyed working with over the years, and Ed Bowie. And they're talking about essentially halos around galaxies. So we know galaxies sort of form as a dish shape, but what they're discovering is things that are sort of over the top and below the bottom. And the importance of that particular material is what they're talking about tomorrow night. So that'll be good. On October, I guess, is it the 14th or 15th? I'll have somebody come in. So it's Saturday.
The 15th.
15th. No, somebody else was telling me it was the 14th, so I was confused. But actually on October the 15th, it's a Saturday. We are open. It's a big open house. It's called EC Day, Earth and Space Exploration Day, and you can come down and visit us. You can actually just come to the school and see. We've got over 20 exhibitors that will have tables and things like that. I will be in the Marston Theater with my staff and my team, and we'll be presenting programming in 3D. So you can come see that, and it is just inclusive all the way from 10 until 2 o'clock in the afternoon, and Saturday the 15th. You don't need to know anything other than just show up and enjoy. And so I just thank everybody for attending. I really love your longstanding support for our particular program. We'll see you in 2 weeks. We'll be talking a little bit more about night sky and night sky objects, and maybe I will actually get that camera on Jupiter in 2 weeks. That would be kind of fun to see, and we'll see where we go from there. So thank you very much for attending, and unless I forgot to say something and anybody wants to chime in, I'm going to say good night and thank you for attending, and we'll see you in 2 weeks. Thank you. Bye-bye.